Quantum numbers. Bohr's model worked for single electron atoms. And notice the title here, right? Bohr fixed the old atomic model, but now there are issues with the Bohr model. So it works for hydrogen, but also singly ionized helium, doubly ionized lithium, triply ionized beryllium, etc. In other words, atoms that only have one electron. But the spectra of multi-electron atoms reflected more energy levels than were predicted by the Bohr model. Explaining multi-electron atoms required extending the idea of wave-particle duality to electrons. So just as light can act like a particle or wave, so too can electrons. Schrödinger's wave equation. Schrödinger wrote an eponymous equation that is used to solve for electron waves confined to an atom or molecule. These solutions are the basis for much of what follows in this course. His wave equation describes the probability of finding an electron at a location. An electron's location in an atom cannot be known, just the probability of it being at a location. Schrödinger received the Nobel Prize in Physics in 1933 for the development of his equation. Since we cannot say exactly where an electron is, and that's quantum mechanics, the Bohr picture of the atom with its electrons in neat orbits cannot be correct. Quantum theory describes an electron probability distribution. The figure over here shows the probability distribution for the ground state of hydrogen. The probability, and I'm saying that word a lot, but that's kind of what we're doing here, of finding an electron at a location is represented by the density of the cloud at that location. So closer to the nucleus, hopefully you can see that's a bit darker, so you're more likely to find the electron there. And then out here, you can still find the electron, but the probability is a lot less. Solution to Schrödinger's wave equation, and that's a college activity. We're not doing that in high school. That takes the form of sets of four quantities, n, l, m sub l, and m sub s, and those are called quantum numbers. Together, they specify both the energy and the probable location of an electron in an atom. No two electrons in an atom can have an identical set of quantum numbers. N, the principal quantum number. Well, that's the same N that we use in the Bohr energy levels. We call that the shell or the energy level. The energy levels all have negative energy, and the lowest energy, which is the greatest magnitude of negative energy, is for n equals 1. Sorry, that's a little confusing, but we've said that earlier, and hopefully it's starting to sink in. As n increases, the shells are farther from the nucleus and have greater energy, in other words, less negative energy. L is the angular quantum number. There are subshells housed within each shell. The higher the energy of the shell, the more subshells it houses. The number of subshells is equal to the principal quantum number. There's n. So the n equal 2 shell has 2 subshells, the n equal 3 shell has 3 subshells, etc. The subshells corresponding to subshell 1, 2, 3, and 4 are labeled by these letters, S, P, D, F. M sub L, magnetic quantum number. Orbitals are now housed within each subshell. The magnetic quantum number determines the spatial orientation of the orbitals. The S subshell is spherical, so it has only one orientation. I mean, you can rotate a sphere and it'll still look the same. So there's only one orbital in the S subshell. There are 3 orientations for the P subshell, 5 for the D, and 7 for the F. That's the number of orbitals within each of the subshells. The shapes of these orbits, which show the probability of finding the electron in the orbital, are shown on the next slide. So we only have one S subshell because there's only one orientation of a sphere. You rotate it, it looks the same. For P, you've got these double lobes here that can be pointing in each one of the axes, X, Y, and Z, so you have 3 of them. D, a little more complex. You're pointing in different directions, but you also have some extra lobes going on. So that's 1, 2, 3, 4, 5. And then finally, F is the most detailed at the moment. You've got 7 choices, and you have more lobes and different orientations. But look at this. If you go down right here, that 0 one, all kind of the same, aren't they? So again, what does this tell you? That tells you the probabilities of finding where the electron is. One more quantum number, the spin quantum number, m sub s. In the 1920s, it was discovered that when an external magnetic field is applied to an atom, two electrons in the same orbital do not have exactly the same energy. This led to the fourth and final quantum number, the spin quantum number, m sub s. Every orbital can house up to two electrons with opposite spins. Now, since an electron is a point particle, it doesn't spin, but the name, which relates to the orientation of its magnetic field, stuck. Here's a handy summary of the quantum numbers. Right? Here's n, here's our shell, energy level. Then we have our subshells, the number of orbitals within the subshell, the number of electrons per subshell, and finally we total it up per shell, the number of electrons. So here we go, n equal 1. All you have is one s. You have one orbital, and there are 2 electrons per the subshell. So we have a total of 2 electrons per shell, per the s shell. N equal 1. Then n equal 2, we have a 2s and a 2p. The s again just has one orbital, 2 electrons. The p shell can have 3 orbitals, and that was that picture we showed on the previous slides. And each orbital gets 2 electrons. So we have 6, total of 8 per shell. We go down to n equal 3. Now we have 3s, 3p, 3d, 1, 3, 5 orbitals, and again each one has 2 electrons, so 2, 6, 10 for a total of 18. These are important numbers. We'll see those later when we get to electron configuration. And then we get to n equal 4, right? That's farther away from the nucleus. Now we have the f subshell coming in, 1, 3, 5, 7 orbitals within the subshell. And then we have 2, 6, 10, 14 electrons for a total of 32.